All right, we'll go ahead and get started. Welcome everyone, I'm James Ward. I'm the open source ambassador at Salesforce. So thanks for coming. This will be an introduction to machine learning, and hopefully if you haven't done anything with machine learning or have done maybe a little bit, hopefully this will help you take the next step with it. So I'm a developer, been a developer for a long time, and I got into machine learning pretty recently because Salesforce started acquiring all these different companies around AI technologies and machine learning, and I thought it'd be fun to start to learn some of them. So that's how I dove in, started playing with Prediction.io and working with our Einstein team on some fun stuff. So I'm a developer, I'm new to machine learning, or fairly new to machine learning, so hopefully that'll help you connect with the subject. So first let's talk about how machines learn. So that's my daughter Josie, she's 2. And it's pretty fun to watch how she learns. So if you're a parent, you've probably experienced children who will be sitting in the high chair and they take their food and they drop it on the ground. And what do? We pick it off the ground, put it back on their tray. And so then they're like, oh, this is a fun game. Let me drop it again. And then the cycle repeats. Right? And what they're doing is they're observing the world, then they're comparing it to their expectations. So of course Josie when she drops that food, she wants to see what happens, what's the reaction. And then she analyzes the differences. How is this different from what I expected? And then refines her model of how the world works, and then continues this cycle. And that's how she's building her model of the world and learning. So what about machines? How do machines learn? And it's a pretty similar cycle. So what we do is we take data and we turn that into a model. Then we evaluate that model and take feedback signals, so things that are giving us feedback about the correctness of our model. And then we refine our model and do it all again. And that's the cycle that we're doing with machine learning. So we're going to dive into some details on what that actually looks like. But so what is it? I think machine learning kind of started very simply with all right, we have some data and we're going to just do like a bunch of if-then statements and nest them together and have some sort of decision tree to help us make a decision. But that didn't really work very well. It didn't get us very far. And so now what a lot of our machine learning systems do is they take data, they apply an algorithm to the data, create a model, and then we can use that model for predictions, categorizations, other things. Paul Snively once said that all machine learning is compression. And essentially why we need to create this model is because the data is usually too big to actually make a reasonable decision from just in its raw form. And so what we need to do is distill that data down into something smaller, something that we can easily and quickly ask for predictions and categorizations. The field of machine learning is massive. There is tons and tons going on around all sorts of different types of machine learning. There's supervised learning and many branches of that, and reinforcement learning and unsupervised learning, and all these different branches in the AI universe. So it is massive. That was one of the things that as a developer getting in this world, I'm like, oh my God, like this is really overwhelming. So I'm going to try to break it down a little bit. So first, if we start with our use cases, we kind of divide this up into layers. We've got use cases, we'll drill into those. So use cases could be like rate leads in terms of how likely they are to close. So at Salesforce, this is something that we've built on our Einstein platform, is the ability to rate leads. Pretty common thing to apply machine learning to. Categorize this text in some way. Is it offensive or not offensive? Is it positive or negative sentiment? Those sorts of things. That's categorization. Recommend products, right? That's a good use case for machine learning. Detect anomalies. So these are just some of the use cases, but the way that we can actually accomplish those use cases is by using some core methods. So there's really 4 core methods that we can use in machine learning to help our machines make a decision for us. And if what you're trying to do doesn't fit with one of these methods, then what you're trying to do probably isn't a good fit for machine learning. So I talk to salespeople a lot who are like, give me some crazy problem and say, oh, can Einstein do this? And I'm like, well, you probably don't have enough data. You know, it's like, can Einstein predict what the next number in a quantum random generator will be? It's like, no, probably not. Like, it would be awesome if it could, but maybe in the future, we don't know. But so if what you're trying to do doesn't fit into compression, classification, regression, or reinforcement, then maybe machine learning isn't what you should be using there. So I'm going to be talking mostly about a type of machine learning, a piece of machine learning called product recommendation, also called collaborative filtering. So that's one of the things that as I got into this area, I realized that there's all these terms and words that like made no sense to me, and it turned out they were usually pretty easily explainable. So as I go through, I'll try to identify some of the terms as how I would say it and then how like the machine learning community says it. So product recommendation, they call collaborative filtering. So what we're doing in collaborative filtering is we're taking some likes. So we've got some users, they're liking items, products, whatever, and we're going to use some fancy heavy math to generate a model, and then from that model we can make predictions to tell you, here's some other things that you might be interested in. So let me show you a demo of what this could actually look like. So, and this is actually like real, it's using Prediction.io, and I'll talk a little bit about the technologies in a minute, but this is a demo application called Dreamhouse, and it's something we've built all sorts of stuff around. But what we can do in Dreamhouse is go see a bunch of properties. So we can go see, okay, here's this beautiful property, and we can go in and favorite that property, right? And then we can go back and go to our favorites and see there's our list of favorites, right? And so other users have done this in the system, and so then because I've favorited things and other people have favorited things, now we can use that product recommender to actually go get some recommendations. So now it's going out and saying, okay, based on what you've favorited and what others have favorited, here's some other properties that you would also be interested in. So I'll show you some of the code for this in a little bit, but all the code is available on dreamhouseapp.io. Okay, so that's our little demo that we're going to talk about how that actually works and how I used machine learning to build that. So pieces of the puzzle for that particular demo, Prediction.io is my open source machine learning server. I've run it on Heroku using Heroku Postgres and Heroku Connect and Apache Spark and Spark ML. So Spark ML is really the thing that's actually doing the machine learning, and that's the piece that we're going to dive into in a lot more detail. Okay, so let's talk about how we do product recommendation. And my hope for this is that you'll see how one algorithm works, and that'll help you understand how other algorithms work as well. So we're going to dive into the product recommendation, how that actually works. So with product recommendation, let's start with how humans would do product recommendation. So what I've done is create a matrix of properties and users. So user 1 likes property 1, user 1 likes property 2, user 2 likes property 2, so on and so forth. So what we can infer just as humans from this is that user 1 would probably like property 3 because there's a correlation between what user 1 and user 2 like. So because they have something in common, they both like the same sorts of things, that we can infer that because user 2 also likes property 3, that user 1 should like it too. And then we could go further right down the matrix. User 2 should also like property 1, and they should like property 4 due to the correlation with user 3, so on and so forth. So that's kind of the direct correlations, but then there's another set of correlations that are like the second tier correlations. So user 1 should probably like property 4 because user 1 had something in common with user 2, had something in common with user 3 who liked property 4, right? And so just as humans, we can begin to put together this model and figure out what things we should recommend to these different users. So when we're looking at product recommendations, we, especially as in like this real estate example, what we can imagine is that every property has some traits or some features is what the machine learning folks like to call these, some features. And so if we knew what the features were for all the properties, like property 1 was near a park and had was by a good school, property 2 was 4 bedrooms, so on and so forth. And then if we also knew what the user features were, so what the users wanted when they were looking for something to like, then we could actually have a much better idea of what we should recommend them. Actually, we would know exactly what we should recommend them, right? So by being able to have all these features, if you had these features in your system, then you wouldn't actually need any machine learning. If you have this information, you essentially could just do a search of this data. But where machine learning comes in is when we don't actually have those features. So that's what we're going to talk about, is how we get there. So we've got likes. That's the piece of data that we have. Users have liked properties. And let's say we did have the property features. So let's say we did have that property 1 was near a park, right? So we could actually take the like data and take the property features and compute what the user features are. So we can go from likes and property features to our user features. So for example, if user 1 likes property 1 and property 1 is near a park, then we can determine that user 1 likes things that are near a park, right? So that's just the way that stuff works. And then likewise, if we have likes and we have user features, so we know what the users like, then we can determine the property features. So we can go either way with those, right? But remember, we don't have the user features or the product features in this case because we're doing machine learning. Okay, there's another cool thing here, is that if we have the property features and the user features, then we can get to the recommendations. So, and this is, again, is just math. So if we know that property 1 is near a park and we know that user 1 likes things that are near a park, then we can recommend to them to user 1 property 1. So we know that there are these correlations there and can map these mathematically. This ends up just being simple matrix math. Okay, so we can develop these mathematical models that will do this for us. So then, if we have likes, remember that's all we actually have in this system. How do we get from likes to our property features and our user features? And that's exactly what our machine learning system is going to do for us, is give us a way to create those property features and user features. So how does it work? Well, in this case, I'm using an algorithm called the alternating least squares. So alternating least squares is a mathematical algorithm that was developed many times. I don't know who initially came up with it. But it's the way that we actually can develop those two feature matrices that we need. So the way that it works is what we're going to do is just actually generate some random data into a matrix. So we're starting with our user features matrix. So we're generating some data into this matrix. So we're just randomly saying, okay, user 1 likes to be near a park, right? We don't actually know that, but we're going to say that. And then what we're going to do is remember we have our likes. So we're going to take our likes, that's that green chart in the middle. So we're going to take our likes, and remember we can do that computation from our user features and our likes to get to our product features. Okay, so we've just done the math to make that transition from random data with likes to property features. Now, this is, at this point, just random property features, right? These are not real. So what we do is we go through a cycle where we compare this data. Well, actually, it's not entirely random because we did base it on user likes. Part of that equation was based on actual reality. So we generated the property features. And then what we do is we go through this again, but in the other direction. So we actually take the property features that we generated, which were kind of based on randomness and kind of based on reality, and we take that with our likes again, and then get a new matrix for our user features. So we've generated random user features. We've used that with our likes to get our product features, and then we've taken that product features that we calculated, and we apply our likes again and get a new user features. And then we do this again, so we repeat. And what we eventually do is converge to a model that fits our training data set. And our training data set is the likes that we gave to the system. So our model is converging over time, over iterations through the cycle, to something that fits that data that we gave it initially. But now, here's the cool thing, is that we've got our features, our user features, and our product features. And remember, we can use both of those to generate recommendations. So this is our model. This is our model, is our user features and our product features. So up to this point, I've been describing these features in terms of near a park, has a nice view, so on and so forth. But it turns out, here's the magic in machine learning, is we don't have to actually know what those features are. We can just say that these features exist, and our model will fill them with data to fit the training data that we gave it. Okay? So the features don't have to have names. We don't even have to know what they are. They don't even have to exist in our training data set. And that's what the machine learning part of this is doing, is it's creating these features, filling them in. And so we could have one feature, we could have hundreds of features, doesn't matter. But this is where we get into model tuning, is that how many features we want can affect how accurate and how quickly we can arrive at a model that accurately fits our training data. Okay, so that was alternating the least squares, which I tried to distill down into something simple, but is certainly a bit complex. So any questions about alternating least squares before I go on? We're going to see it in code in a minute. So yeah.
Do you know that it will stop? It will convert?
Oh, so what you do is you tell it how many iterations you're willing to spend on it. And then what you can do, once your model is generated, you can test your model to see how far off it is from the training data or some other data set that you gave it. And so that's definitely a big part of machine learning, is generating models and then testing models to see how correct they are against the training data that you have. Yeah. Yeah, so you definitely have to specify max iterations. You don't want it to run forever. Yeah?
You have to specify maximum iteration. That means at a certain point, they stop learning. Am I getting this right?
Yeah, so that's a great question. So in this type of machine learning, what we're doing is we're taking a data set, we are applying this algorithm to get to a model, and then we use that model, so we deploy that model into production, and we use that model. But what you're pointing out is that the problem with that is that our data is actually changing over time. And so what typically is done to address this is we have some batch process that's regenerating a new model based on the new data that's in the system.
So it's continuously
But it's batch mode. And I think that this is certainly one of the challenges that the Einstein team has been working on at Salesforce, is to get away from this okay, we're going to nightly generate a model that may be out of date an hour after we deploy it, right? And so there certainly are some challenges, but this is the traditional kind of easy model for how we do it.
Thank you.
Yeah, good question, thanks. Okay, any other questions before we go on? See some code and stuff. Okay, so just to recap, we took our likes, that was our training data set, and we applied the alternating least squares algorithm, which gave us back our property features and our user features matrices. And then from those matrices, we can calculate recommendations. So there's another part of this, which is, okay, so I've got these two matrices, the property and user features. Now, how do I actually get a recommendation out of that? So the way that we do that is we do dot product math on these. And so we take, let's say, property 1 and user 1, and we go through every feature, and we just essentially add up the values in that chart. And that gives us essentially the probability that this user matches with that given property. And so if we actually do that process for every single slot in our matrix, then we can calculate what's called the matrix factorization model for this. And this can actually be a pretty heavy computation, because we're going through every row and every column for like the whole data set. And so if it's a large data set, oftentimes it doesn't actually make sense to generate this model. Previous versions of SparkML would just give you this model out of the box, and I think they stopped doing that because it got pretty heavy with large data sets. So now the only thing that they give you by default is the user features and the product features. And if you do want the matrix factorization model, then you have to go build that yourself, essentially. Okay, so one of the nice things, remember I said earlier that Paul Snively said that all machine learning is compression. So here's where we can see some of that coming into play, is that if we took our user features and our property features and we calculated that, that matrix factorization model, then just if we had 10 by 10, that would be 100, right? 100 different things we have to store. But if we only store our property features and our user features, then we can actually save a lot of space in terms of the matrix that we're actually storing. So I don't know, I think I reduced that to three times 3. Anyways, it's a whole lot better, a whole lot more efficient to not calculate that matrix factorization model and just save your features and users. So usually you would save these into a big data store, Hadoop, whatever, both of these charts, and then you'd be able to use them whenever you want. Okay, so let's dive into some code to see how that actually works in Spark. So I have a demo project here that is the one that I use for the Dreamhouse application. And I'm going to walk through a bunch of the code for how this actually works and then how I actually test it. So let's see. So first thing I have is a train method. So my train method is going to take a sequence that is a tuple here of user ID and then the property ID. So these are likes. This user liked this thing. And I'm just using essentially a binary rating here that is a like. But you could certainly instead have a third parameter, which would be like stars. So if you have 1 to 5 stars on something, then you could have a third parameter that would be that rating. But in my case, my rating is either off or on. So I just have the user ID and the property ID. Then I have some parameters to the ALS alternating least squares method. So there's regparam, which is how much weight do we want to place on extreme values. Then there's the rank, and rank is the number of latent features. So that's how many features do we want in those feature matrices. So I default that to 3. So that means that for each user, and we want to know the features that they like, then we're going to have 3. We're going to say that there's 3 different things that distinguish what they like. So as that number goes up, your model can be more accurate usually. Then here's our max iteration, so I default that to 10. So that means by default I'm going to run through that alternating least squares 10 times. Okay, and then what this outputs is an ALS model. So that is really just a holder for those 2 matrices, the product features and the user features. So then what I'm going to do is, because this is Spark, I'm going to convert my likes to a data frame. And my data frame has 2 columns initially, a user and an item. Item is the default name that Spark wants. We could rename that if we want, but those are my 2 initial columns. But then I need a rating column, because remember I didn't specify a rating. It's either on or off. And because it's a like, we know it's on. So what I'm going to do is just add a column that is rating, and its value is going to be 1. So I'm just leaving out all the data that's anyone that didn't like anything, we don't care about them. Okay, so then what I'm going to do is initialize the alternating least squares stuff from Spark, specify those parameters, and then here's the magic, als.fit ratings. So I'm giving it these ratings to the ALS fit method, and then that's what actually is going to go and do all that computation, going around and around for 10 iterations by default, and calculate a model, which is the product features and the user features that fit the training data, which is the ratings. So it's going to generate that. Okay, so there's a whole lot of math that happens when I run that als.fit. In the case of my small data set, not so much, but a whole lot of math. There's some pretty serious equations that go into how that actually works and how it converges and all that. So that's my train method. Let's go flip over to my tests here. And I've written some tests. I've learned that machine learning world, they don't often write automated unit tests and stuff for things, but I wanted to do that so that I could actually test that this thing worked as expected. So I want to show you the tests that are here. Okay, so for my tests, what I've done is I've put together a simple matrix of users and properties, and what in my in my training data set, I've said that user 1 likes property 1, user 2 likes property 2, so on and so forth. So then I've just charted out here in ASCII what I think should be the result from the predictions in terms of what they should like. So user 2 should like property 1, and so on and so forth, right? You can see all that there. Okay, so then I need to actually, I can't take ASCII and give it to this thing. So there's my actual matrix of, all right, user 1 likes property 1, and user 2 likes property 1. Is that right? Or property 2 is liked by user 1 or something. Okay, so there's my matrix. So then what I'm going to do is actually test this thing. So I'm going to run the train method on from my Dreamhouse recommendations. And then I'm going to test a few things just to make sure that the training actually worked as expected. So the first thing is that the user factor rows, so this is not the columns, this is the rows in the user factors, should be 5. And that's because I have 5 unique users there, right? And same with item factors, should have 5 rows because I have 5 properties. So you'll see that the API calls this item factors to make it work with whatever you want to recommend, but this is my property features. And you'll also see that they call it factors, so another word for features in this space. Okay, so then my next test is to go to my user features, get the first row, and what I get out of that is a sequence of long, which is my features. And here's where I'm actually getting out the features from this thing, from my training, from what my model is, my user model, and I'm verifying that the number of features equals 3, which should correlate with this 3 here, which is the default number of features that I've specified, right? So that's what I want to test first, and let's go actually just run this thing so that we can verify that this all works. So it's going to take just a little bit to run this because it has to spin up Spark and then do all the matrix math on that. So, but then what we should see is that it's going to pass. But while that's doing that, there we go, it passed. I want to show you how we can actually look into this stuff to see what it actually looks like. So there's some stuff in Spark where we can say model.userFactors.show. And I'm going to tell it not to truncate the output. And let's also do the item factors. And then let's just rerun that one. And now we'll actually be able to see what those models look like. All right, so I'll take a second to start up Spark and then run that. But what we'll see is our model here. So what we're going to see is our actual model. This is the thing that Spark has generated using alternating least squares, and then we'll be able to use for predictions. Okay, so there we go. There's our features. And what you'll see is that, so this is the first one is the user features. What we'll see is that user 1 has these 3 features. So remember, we just made up these features. You know, this could be the view, this could be the number of bedrooms, whatever. We don't know at this point. We don't know because we don't have that data. But what we've done is we've generated values, and these values go from 0 to 1. So essentially this is saying user 1 really likes whatever this feature 2 is. So again, we don't know what that feature actually is. It doesn't matter. But user 2 also likes that feature. So does user 3. User 4 kind of likes it, right? And user 5, not at all, right? So we can see these values. They really mean nothing to us. This is just this generated model. And then the same thing for the user features. I guess those don't go 0 to 1. They go a little above 1 sometimes. Maybe to 2, I don't know. Okay, so there we go. We see our user features too. Okay, so that's our training, and I'll remove that. So that all worked as expected. But then we have our model, and now we want to actually make predictions against it. So let's go down to our next test, where we're actually going to use the predict method. And I'll go into the predict method so you can see how this one works. So for this one, what we're going to do is we're going to pass in our model, and then we're going to pass in the user that we want to query. So this particular predict method only takes a single user, but you could certainly cut this data up however you want to. You could do multiple users. You could say, give me the top top users, give me the top products, all that kind of stuff could be done. But we're just going to say for a given user, give me the items that they will like. And then number of results that we want to get. And what this returns is a map from int to float. So that is the property ID, and then the likelihood, the value, the likelihood that the predictive value, so how likely they are to actually like that property. All right? Okay, so now what we're going to do is go to our model, and there's this convenience method here, recommend for all users, which is going to do that matrix factorization model for us on those two, the item and the property features models. And it's going to get us the number of results that we're looking for. So it's getting us the top, by default, the top products. And then we're telling it to filter out, because we really only want to see the user that we're making predictions for. And so we're telling Spark to filter on the column user and then match on the user that we're querying. So what we get back from that is this data set of row. And what we want to do is then convert this thing to what we actually, this data in the form that we want, which is this map from int to float. So I have to do some math here. So we actually get the way that the data looks when it comes back is that it's a single row which has the user ID, and then it has an array of arrays, which each array is essentially a tuple of the property and the prediction. So essentially what I'm doing is just parsing that data out to get me my map into float. Okay, so that's our predict method. So let's go take a look at a test for this one. So here's just a basic prediction. We're calling the predict method. We're saying, here's your model that we generated. And then your query user is 3. So user 3 up here, we can see user 3 should be interested in, this way, actually. User 3 should be kind of interested in property 2, and they actually liked property 3 and property 4, so they should definitely be interested in those, right? But we should get a good high number for property 2. Okay, so my test down here, what it's doing, and the number of results is 10. Okay. So I'm checking to see that my size of my results is 5, and the reason why it should be 5 is because I only have 5 properties. So even though I said num results 10, it shouldn't be able to give me more than 5 property recommendations because I only have 5. And then we're going to go through and test this to make sure that it fulfills our expectation, which is basically just checking to see does it look like what we see on this user 3 column, right? And let's go actually view what our results look like. And I'm going to print those out. Result. OK, and println. I guess print works also, but we'll do println. And then let's run this one. So that's going to go off, retrain the data, and then call the predict method on it. So that's going to take 15 seconds or so to run. For some reason, I was running these in SBT before. If there's any like SBT experts or Spark experts, I need some help. For some reason in SBT, when I ran them, it would take like 20 times longer to run an SBT for some reason. So thanks to Russ somewhere over here who helped me. He's like, why don't you just run it in IntelliJ? And I did, and it ran a lot faster. So there we go. OK, so there's our prediction, which is just showing us, all right, prediction for property 5 is Prediction for property 1 is pretty good. Prediction for property 2 is really good. Prediction for property 3 is basically like, yep, absolutely. And same with 4. And if we look back at our model for user 3, we should see that that basically fits the data that we're seeing up there. So you see that it has created this model that is then converged to something that fits the training data set. Okay, then there's more tests down here. I'll just walk through these real quick. So there's some, what I want to do is test to make sure that the parameters that I can specify when I create this model, that they actually are having the effect that I want. And so the first one is reg params, and reg params, I don't really know what that does in the algorithm, but I do know that the model should be more accurate for lower reg param numbers. And so I'm just creating two different models. And then there's this really cool stuff in SparkML where I can check to see, all right, how close did this model that was generated fit to the matrix that I expect. And the matrix that I expect, I actually fill out with all the likes and all the not likes, essentially. And so I'm checking to see, does the model that's generated fit that? And the way that we do that is with this regression evaluator, where we're doing a root mean squared error analysis on that. And this gets into some math that I definitely don't understand. But essentially what we're doing is seeing how far does the generated model deviate from what we expected. And what we can then do is compare. So we do the root mean squared error for both of these, and we check to see, in this case, the lower reg parameter should be less than the higher reg parameter, right? It should be lower error than the one with the higher number. And I'll just run all these so you can see that, sure enough, all of my tests pass like a good developer. But it works. And then I'll go on to the next one. So the next one is higher ranks. So the ranks are the number of features that we want in our model. And so I first do 1, and then I do 5, and then I do my root mean squared error and say that, yep, when I did, I called it 10, but it should actually be 5 down here, that my 5 should have less error than my one with 1, because I should get more accurate with more features. Okay? And then finally the last one is that I should be more accurate with more iterations, and that in fact is true as well. So in machine learning, one of the challenges is that if we had infinite resources, compute and storage, we could create a model that was just absolutely perfect for our data. But oftentimes we don't have infinite compute resources. And so what we need to do is figure out how to balance the amount of time that we spend generating models. So that's doing what's called model tuning, and figuring out, okay, how can we kind of minimize the resources that we're putting into this, but maximize the correctness of the model that's being generated. And so that's where that machine learning gets into a lot more data science and figuring out how to tweak all these different knobs to optimize things best. But so that's what is called model tuning. And a part of that is model selection, being able to select the best model for a given case. So there's all sorts of caveats to this whole world. Like sometimes you can get a model that essentially is overfit. So that's when, if I basically was recommending all products to everyone, then because my model actually was just like, hey, everyone likes everything, then that would be overfitting. And so that's a challenge that you have to look out for as well. Okay, so there we go. All my tests pass, and let me show you where you can go get all that code. So if you go to dreamhouseapp.io, and I don't know why it's searching for that, but there we go. And then go to the Apache Prediction.io one down here. You can see a fun demo, and then get the code down here at this repository. So that's the code that I actually use for the Dreamhouse app there to do the recommendation for Dreamhouse properties. Okay, so that's all the code for that one. Okay, so that's all I got. Questions? Yeah?
So how does the code calculate the derivatives, the ALS algorithm?
How does the ALS algorithm actually do the math? Oh, that's way beyond me. I'm sure that there's some of our Einstein team in here that can answer that for you, but I actually don't know the math. What I've wanted to understand the math, but it's some pretty heavy statistical analysis stuff usually, and I don't know that part of math very well. And so what someone actually recommended to me if I wanted to understand the algorithms was they said, go look at the Python implementation of these algorithms. And the Python implementations are usually pretty easy to read and understand how it's actually working. And it's often a lot easier to understand the algorithm from the Python implementation than actually the mathematical models that are underneath all that. So that was the recommendation I received on if you really do want to dive in deeper to the mathematical models under that. Yeah. Okay, other questions? All right. All right, well, thanks everyone. I hope that was useful, and I'll be around later if you have other questions. Thanks.